Hello everyone, so welcome to the paper discussion session for part test 16. So this is the first question over here. So Me2SiCl2 on hydrolysis. So generally SiCl4 reacts with Grignard reagent resulting in the formation of R2SiCl2. So this is the bonding pattern in R2SiCl2. Now this molecule will undergo hydrolysis, and as a result what will happen? The anionic part of water, OH minus ion, will behave as a nucleophile in this reaction. It will attack the silicon, and as a result SiCl bond will get dissociated. So it will result in the formation of R2SiOH2. So this is a monomeric unit that I am getting, right? Now the monomeric units that is formed in this reaction, all this will combine, resulting in the formation of long chain silicon polymer. The monomeric units will undergo polymerization basically, resulting in the formation of long chain silicon polymer. So the polymerization will actually occur in this manner. So this is one molecule over here. Similarly, there will be more neighboring molecules like this, right? Again SiRROH. So in this way the monomers will combine along with the elimination of water, and that's why we are supposed to get long chain polymer like this. Obviously the hydrogen from both the ends will also be removed out because of elimination of water. So obviously finally we will get this type of long chain polymer, right? This type of long chain linear polymer we are supposed to get. And in this polymer, which is the repeating unit? In this polymer the repeating unit is actually R is the alkyl group, again O. So this is a repeating unit. This unit will repeat n times, right? So that's why in this case alkyl group is nothing but the methyl group. As per the question here, the alkyl group is nothing but the methyl group, and that's why C is the correct answer. Let's proceed to the next question. Which of the following halides is least stable and has doubtful existence? Now carbon, silicon, germanium, tin, lead, all these are group 14 elements. So what is a stable electronic configuration? What is the electronic configuration of group 14 elements? That is actually NS2 and P2. So for carbon, what is the principal quantum number of the outer motion? That is 2. For silicon, 3. For germanium, 4. For tin, 5. And for lead, the value is 6. Value of the principal quantum number of the outer motion. So for lead, what is the electronic configuration? 6s2, 6p2. That is the electronic configuration of the outermost cell. Now we know in thallium, bismuth, and in lead, lead and bismuth, there will be inert pair effect. In thallium, what is the electronic configuration? 6s2, 6p1. In lead, what is the electronic configuration? 6s2, 6p2. And in bismuth, the electronic configuration is 6s2, 6p3. Electronic configuration of the outermost shell. For bismuth, the stable oxidation state is +3, for lead it's +2, and for thallium it's +1. Clearly from the values of the stable oxidation state we are getting an idea that only the 6p electrons, they are participating in bond formation, and the 6s electrons are basically inert to bonding. That's why they are not even contributing in the oxidation state. Now this is known as inert pair effect. Or relativistic effect. Now in relativistic effect, actually what happens? So there will be contraction. There will be relativistic contraction of the 6s electrons. So because of that, the 6s electrons, they will be shifted closer to the nucleus. And as a result, the 6s electrons will experience large amount of force of attraction from the nucleus. So because of that, the 6s electrons are tightly held. So that's why they cannot participate in bond formation. Now consider the option D over here. In PbI4, there are actually 4 PbI bonds. For the formation of 4 covalent bonds, obviously 4 unpaired electrons are required. 4 unpaired electrons are required. Yes. Now in lead, this is the orbital picture diagram of the outermost shell, 6s and 6p. So 1, 2, 3, 4. So for the formation of 4 covalent bonds, 4 unpaired electrons are required. So obviously I need to excite the electron from 6s to 6p, but this excitation will not be favorable because of the contraction of the 6s orbitals. The nucleus will try to pull the electron cloud of 6s towards itself, and that's why the excitation from lower energy level 6s to higher energy level 6p will not be very much favorable. Since the excitation is not favorable, we will not get 4 unpaired electrons. So that's why 4 covalent bond formation will also not be possible, and that's why PbI4 cannot even exist. Right? So easily we can explain this with the help of relativistic effect. So obviously only 2 electrons will participate in bond formation since the stable oxidation state of lead is +2. So Pb2 plus will combine with 2I minus, resulting in the formation of PbI2. So that's why D is the correct answer for this question. That is the least stable substance and it has doubtful existence. Let's proceed to the next question. Now BF3. In boron, how many electrons are present in the outermost shell? 3, right? So all the 3 electrons will participate in bond formation. So boron, what is the steric number of boron in BF3? Number of sigma bonds 3 plus number of lone pairs 0, steric number 3, sp2 hybridization, so trigonal planar. Now obviously BF bond is polar in nature, and the bond pair moment or the dipole moment generated by the bonds will be acting in this direction, from boron towards fluorine, from electropositive substance to electronegative substance. So these are the directions of the bond pair moments, right? Directions of the bond pairs moment. Now these two dipole moments which are acting in the downward direction, these two will get added up, and as a result the resultant dipole moment will be formed in the downward direction. The resultant dipole moment will be obtained in this direction, in the vertically downward direction, right? Now this value of dipole moment that is generated by these two adjacent bonds will be exactly cancelled out by the dipole moment acting in the upward direction. Obviously this dipole moment is also generated because of BF bonds, and this is also generated because of the same BF bond. Since the natures are same, that's why their magnitudes are also same. So if the magnitudes of two vectors are same and if they're having opposite direction, so after vector addition, what will happen? The vectors will get cancelled out, and as a result overall dipole moment of this molecule will be 0 and the molecule will be non-polar in nature, right? Now in case of NF3, for nitrogen, how many electrons are present in the outermost shell? 5, right? So 2 electrons, they are behaving as lone pairs, and the remaining 3 electrons are participating in bond formation. Again the bond pair moment will be acting in the downward direction. So again if I do the resultant vector, if I add up all these vectors, I will get the resultant vector again in the downward direction, and the lone pair moment in this molecule will be acting in the upward direction. Now clearly we know that the lone pair moment is greater than the bond pair moment. So the vector that is produced in the upward direction, that is having more amount of magnitude than the vector acting in the downward direction. Upward direction, that is nothing but the lone pair moment, the dipole moment because of the lone pair of electrons, and in the downward direction we are getting the lone pair generated by the bonds, right? So obviously there will be partial cancellation of dipole moments over here. So overall the resultant dipole moment will be acting in the upward direction, though its magnitude will be reduced, and so dipole moment ka value will not be equal to 0, and that's why this molecule is actually a polar molecule. So obviously since BF3 is planar, that's why its dipole moment is 0, and since NF3 is pyramidal, that's why dipole moment is non-zero. So that's why NF3 is actually a polar molecule. So D is the correct answer. Let's proceed to the next question. So we know higher the value of oxidation state, higher is the acidic character. So there are 5 oxides of nitrogen which are provided over here. So in N2O5, what is the oxidation state? +5. In NO2, what is the oxidation state of nitrogen? +4. In N2O3, what is the value of oxidation state? +3. In NO, +2. And in N2O, nitrogen is present in +1 oxidation state. So clearly we are able to see higher the value of oxidation state, higher will be the acidic nature. So that's why this is the correct answer. Although these three oxides are acidic in nature, the remaining two are neutral. So based on the concept of oxidation state, we can determine the acidic nature. Clearly, when we are moving from left towards right, we are able to see increase in the value of oxidation state. So there will be increase in the acidic nature as well. So that's why B should be the correct answer. Let's proceed to the next question. Mercury is liquid at room temperature. In mercury, there is no unpaired electron. Okay. Now, in mercury, what is the electronic configuration? That is actually xenon 4A14 5D10 6S2. Clearly, we are able to see that all the electrons are actually paired up. So there is no unpaired electron in mercury. No unpaired electron is mercury. And we also know the extent of metal-metal bonding, that is directly proportional to number of unpaired electrons. Extent of metal-metal bonding is directly proportional to number of unpaired electrons, right? Since there are no unpaired electrons, so easily I can conclude that the extent of metal-metal bonding in mercury is very much less. So that's why the force of attraction between the metal atoms will also be less. The force of attraction between the metal atoms will also be less. Since the force of attraction between the metal atoms is less, so easily I can conclude that the metal atoms, they are actually far away from each other. Since they are far away from each other, that's why they exist in liquid state. Yes. So mercury is liquid at room temperature. It is a correct statement, and that is because of the weaker metal-metal bonding. In mercury, the force of attraction between the metal atoms is very much less because of the absence of unpaired electrons in mercury, right? So both the statements are correct. So that's why A is the correct answer. Next, basic character of transition metal monoxides. So 4 metals are provided over here: titanium, vanadium, chromium and iron. So in case of titanium, the atomic number is 22, vanadium 23, chromium 24 and iron 26. So as we are moving from left towards right, there is increase in the value of atomic number. So there will be increase in the value of effective nuclear charge as well. So effective nuclear charge is equals to Z atomic number minus shielding power. Across the period, there will be less increase in the value of shielding, but there will be more prominent increase in the value of atomic number. So overall, there will be increase in the effective nuclear charge as well. Now, from this, we can clearly conclude among all the following elements, the Z star of titanium is very less. Z star of titanium is less than Z star of vanadium, less than that of chromium, less than that of iron. Now, whenever we now metal oxides actually react with water to form metal hydroxides. Right? So MO bond, that will be converted to MOH bond. So again, titanium, if I dissolve that in water, again I will get titanium hydroxide. This type of linkage will be there. Now, since the effective nuclear charge of titanium is less, so titanium will not be able to pull the electron cloud of TiO bond toward itself. So what will happen? Because of the higher electronegative value of oxygen, what will happen? Oxygen will try to pull the electron cloud of titanium oxygen bond toward itself, and as a result there will be elongation of this bond, and because of that the bond will become weak. So if I supply less amount of energy, the bond will get dissociated, and after that it will result in the formation of titanium cation and OH minus anion. It will result in the formation of cationic part along with the formation of OH minus ions. Since OH minus ions are getting liberated, and that's why titanium oxide is the most basic oxide over here, right? In case of iron, the effective nuclear charge is comparatively high, so that's why FeO bond is sufficiently strong. So that's why the electron cloud will be pulled by both oxygen and iron. So there is less probability of elongation of the FeO bond. So there is less probability of dissociation of FeO bond as well. So in case of titanium, since the value of effective nuclear charge is less, that's why the nucleus of titanium will not be able to pull the electron cloud. Because of the higher electronegativity of oxygen, it will pull the electron cloud of titanium oxygen bond toward itself. So that's why there will be elongation of the bond. So easily this bond can be broken down. And because of that, OH minus ions will get liberated. So titanium oxide is having the highest basicity and iron oxide is having the least basicity. So that's why D is the correct answer. Most common oxidation states for cerium. Now for cerium, what is electronic configuration? Xenon, 4F1, 5D1, 6S2. Now cerium actually belongs to lanthanoid series. So we know for lanthanides +3 is the most stable oxidation state, and the stability of this oxidation state can be determined with the help of Born-Haber cycle. So cerium +3 is also very much stable, but if I remove all the 4 electrons, what I will get cerium +4, and cerium +4 will be having the electronic configuration same as that of xenon only. So after removing 4 electrons, cerium +4 is acquiring the electronic configuration of xenon. Again, it is acquiring the stable electronic configuration. That's why cerium +4 is also very much stable. So for cerium +3 and +4 are the most common oxidation states, and that's why B is the correct answer. Let's proceed to the next question. 1 mole of acidified K2Cr2O7 on reaction with excess Ki. Okay. So K2Cr2O7 in acidified medium, it will get reduced to chromium in +3 oxidation state. So chromium +6 will be converted to chromium +3. So what is the value of N factor of K2Cr2O7? So the value of N factor that will be change in oxidation state. Change is 6 minus 3. The value is 3 into number of moles of chromium present in 1 mole of K2Cr2O7. So 6. So from the data of N factor of K2Cr2O7, we can easily conclude that 6 moles of electrons are basically involved for 1 mole of K2Cr2O7, right? Now as per the data, 1 mole of K2Cr2O7 is reacting with some amount of Ki. How much iodine will be produced? So since 1 mole of K2Cr2O7 is actually participating in this reaction, so I can easily conclude 6 moles of electrons are basically participating. 6 moles of electrons. So K2Cr2O7 will undergo reduction and I minus will undergo oxidation. I minus that will be converted to iodine. So I minus from Ki will undergo change in oxidation state from -1 to 0. So what is the N factor for this conversion? The N factor ka value is 1. So it basically signifies that when 1 mole of Ki is involved, 1 mole of electron will also be there. For every 1 mole of Ki, 1 mole of electron will be involved. But in the overall reaction, how many moles of electrons are involved? 6 moles of electrons are involved. So again, if K2Cr2O7 is undergoing reduction by 6 moles of electrons, so potassium iodide must undergo oxidation by same 6 moles of electrons. As per law of conservation of charge, number of electrons lost by it must be equal to number of electron gained. So if Ki is losing 6 moles of electrons, then that 6 moles of electrons will be gained by K2Cr2O7, then only it can undergo reduction, right? So obviously Ki must also lose 6 moles of electrons. Now when 1 mole of electron is there, 1 mole of Ki is involved. So for every 1 mole of Ki, 1 mole of electron is involved. But in the overall reaction, 6 moles of electrons are involved. So obviously 6 moles of Ki must be involved, right? So 6 moles of Ki must be converted to 3 moles of iodine. So that's why 3 should be the correct answer. So C is the correct answer over here. Let's proceed to the next question. Which one of the following pair of elements are called chemical twins? Now, titanium, zirconium and hafnium, these elements, they belong to the same group. Scandium, yttrium and lanthanum, they also belong to the same group. Now in between lanthanum and hafnium, there are actually 14 F log elements. Now chemical properties will be same if the ionic potentials and electronegativities of the elements are equal. So if the ionic potential of hafnium is matching with the ionic potential of zirconium, and if the electronegativity of hafnium is matching with the electronegativity of zirconium, then only we can say that their chemical properties will be same. Ionic potential determines the covalent nature, and electronegativity basically determines the ionic nature. So when we are moving down the group from zirconium to hafnium, there will be increase in the value of principal quantum number. Because of increase in the principal quantum number, there will be increase in size. But because of lanthanide contraction, what will happen? Z star of hafnium will be very much high. So again down a group, because of abrupt increase in the value of Z star, the size ka value will decrease. So because of increase in the principal quantum number, increase in size. Because of increase in the Z star effective nuclear charge, there will be decrease in size. So obviously there will be no change in size overall, right? So ionic potential, the formula is this: cationic charge by radius. Since zirconium and hafnium, they belong to the same group, their cationic charge will be same and their radius will also be the same. Just now we have discussed about that. Because of increase in the principal quantum number, there will be increase in size, but at the same time, when we are moving from zirconium to hafnium, there will be increase in the value of Z star as well. Because of that, there will be decrease in size. So there is increase in size from zirconium to hafnium. Again, there will be decrease in size. So overall, there will be no change in the size. So their radius are also the same. So that's why they will be having same values of chemical, same values of ionic potential. Now again, how we can explain the electronegativity data? Again, when we are moving from zirconium to hafnium, because of increase in the principal quantum number, electronegativity will decrease. At the same time, because of the increase in the value of effective nuclear charge, electronegativity will increase. So decrease in electronegativity, again increase in electronegativity. So overall, there will be no change in the value of electronegativity when we are moving from zirconium to hafnium. So the electronegativity of hafnium will be very much closer to electronegativity of zirconium. Since the values of these two parameters are same, that's why they will be having similar chemical properties. So that's why D is the correct answer over here. Let's proceed to the next question. The correct order of ionic radii. Okay. So yttrium belongs to 4D series, whereas lanthanum, lutetium and europium, these are actually F block elements, right? So scandium, yttrium, lanthanum, and after that between lanthanum and hafnium, europium and lutetium are present. So clearly we are able to see this is actually the principal quantum number of the outermost shell for this period is actually 5. For scandium, the principal quantum number of outermost shell is 4, and for lanthanum and hafnium, lanthanum, europium, lutetium and hafnium, the principal quantum number is actually 6. So down a group, because of increase in the value of principal quantum number, there will be increase in size. So yttrium is having the smallest size as compared to lanthanum, europium and lutetium. Now in lanthanum, europium and lutetium, what are the electronic configuration? For lanthanum, the configuration is 5T1 6S2, for europium 4F7 6S2, and for lutetium 4F14 5D1 6S2. So clearly when we are moving across the period, what we are able to see, increase in the number of F electrons. We know F electrons are poor shielded, right? So that's why from this formula, effective nuclear charge is equals to atomic number minus S. Across the period when we are moving from lanthanum to lutetium, there will be very less increase in the value of shielding power, whereas there will be large increase in the value of atomic number. So overall, there will be increase in the value of effective nuclear charge as well. So as we are moving from lanthanum to lutetium, because of increase in the effective nuclear charge, what will happen? There will be contraction of size. So that's why the size of lutetium is less than the size of europium, that must be less than the size of lanthanum. And overall, this will be the order. right? Overall this will be the order. So this is the order of covalent radius, and here we have to find out the ionic radii. Since they are having the same charge, so that's why their ionic radii will also be the same. Yttrium is having the smallest size, after that lutetium because of very high value of Z star, after that europium, and lanthanum 3 plus will be the largest ion over here. Let's proceed to the next question. Titanium hexaqua 3 plus is purple in color. So again, this concept can be explained with the help of colored wheel. So this is a colored wheel: violet, indigo, blue, green, yellow, orange, red. So purple color will actually lie in this region between violet and indigo, or violet, indigo, blue. So what is the complementary color of this purple over here? So that will lie exactly 180 degree apart from this color. So obviously the complementary color will be a mixture of green and yellow. So that's why D should be the correct answer. Let's proceed to the next question. Number of POP bonds in cyclic metaphosphoric acid. Now this is the structure of metaphosphoric acid. OH, double bond OH, okay, again sorry, so this will be single bond O, double bond OH. So this is the condensed molecular formula of cyclic trimetaphosphoric acids. So clearly we are able to see there are 3 POP bonds, and that's why C should be the correct answer. Let's proceed to the next question. The reduction potentials of chromium, manganese, iron and cobalt are provided. For chromium the value is minus 0.41, for iron plus 1.57, this is the value for manganese. For iron the value is plus 0.77, and for cobalt the value is plus 1.97. These are the values of reduction potential, M plus 3 to M plus 2. These are the values of these are the values of oxidation potentials actually. Plus 3 to plus 2 na? Oh sorry, these are the values of reduction potential. Correct, sorry. Okay, so M plus 3 is getting converted to M2 plus. Reduction basically signifies gain of electrons. So these are the values of reduction potential. So what will be the values for oxidation potential? We know oxidation potential is nothing but negative of reduction potential, right? So for chromium, what is the value of oxidation potential? That should be plus 0.41. For manganese, the value should be minus 1.57. For iron, the value should be minus 0.77. And for cobalt, the value should be minus 1.97. So clearly we are able to see chromium is having the highest oxidation potential. So E0 of M2 plus to M3 plus is the highest for chromium among all the metals present over here, right? The value is actually plus 0.41. Since the oxidation potential of chromium is the highest, that's why chromium has the highest tendency to get converted from plus 2 to plus 3 oxidation state. Chromium has the highest oxidation potential, so that's why easily it can be oxidized from plus 2 to plus 3, and that's why it should be the correct answer. Now let's proceed to the next question. In pyrophosphoric acid H4P2O7, number of sigma and dpi-pp bonds. So H4P2O7, first we need to find out the average oxidation state of phosphorus. So 4 into 1 is the oxidation state of hydrogen, plus 2 into X, S is the oxidation state for phosphorus, plus 7 into minus 2. Total charge will be equals to 0, since the molecule is overall neutral. Minus 2 is the oxidation state for oxygen. So 4 plus 2x minus 14 is equals to 0, or x ka value is equals to plus 5. So in this case, the calculated value of oxidation state of phosphorus is matching with the maximum value of the oxidation state of phosphorus. So that's why, since the values are matching, there will be POP type of bond. After that, we have to draw the molecule like this. We have to put double bonds on both the phosphorus, and after that we need to balance the remaining hydrogen and oxygen with the help of OH, right? So this is the exact structure. So if the value of calculated oxidation state is less than maximum oxidation state, then there must be phosphorus bond, and if the value of calculated oxidation state is greater than maximum oxidation state, then there must be phosphorus oxygen phosphorus bond, peroxy linkage must be present. So in this case, since the values are matching, so that's why POP bond is present. So this is the bridging oxygen over here. So how many sigma bonds are present over here? 1 2 3 4 5 6 7 8 9 10 11 12. So there are 12 sigma bonds. Along with that, how many d pi p pi bonds are present? So there are actually 2 d pi p pi bonds. So that's why D should be the correct answer. Let's proceed to the next question. Which of the following carbonyls will have the strongest CO? Now in case of carbonyl ligand, in the first step, there will be ligand to metal sigma bond, right? And in the second step, there will be metal to ligand pi bond, synergic effect, right? So in the first step, ligand or carbonyl will try to donate the electron cloud from its sigma non-bonding electron to the vacant orbital of metal. In the next step, what will happen? Now after this donation, after the sigma donation, the electron density on metal that will increase, and as a result, metal will try to donate the electron density back to the ligand, back to carbonyl. So obviously the donation of electron from carbonyl will take place from sigma non-bonding, and the acceptance of electron cloud from the metal will actually take place in the pi star orbital of CO. So in the sigma bond, sigma non-bonding orbital is involved, whereas in the pi back bonding, metal to ligand pi back bonding, pi star orbital is involved, right? So clearly, because of the donation of electrons, by the ligand, what will happen? There will be increase in the CO bond order. There will be slight increase in the CO bond order. And after the sigma donation, what will happen? There will be more accumulation of electron density on the metal. So after that, the metal will try to donate the electron cloud back to the vacant pi star orbital of carbonyl, and because of this back bonding, because of the acceptance of electron in the anti-bonding molecular orbital, what will happen actually? The CO bond order will decrease. So higher the extent of metal to ligand pi back bonding, there will be more decrease in the CO bond order, right? So among the following options, manganese is present in +1 oxidation state, chromium and iron are present in 0 oxidation state, and vanadium is present in minus oxidation state. So clearly in manganese, the electron density is the least. So manganese has very less tendency to donate the electron cloud back to carbonyl. Since the probability of this donation of this electron cloud is minimum, that's why there is very less probability of decrease in the bond order of CO as well, very less probability of the decrease in the bond order of CO. So I can say that the bond order of CO will not change much because of very less extent of the pi back bonding. The bond order of CO will not change much. So that's why CO will be having the strongest bond in the first complex. In the third complex, in vanadium, the electron density is very high, and because of that, pi back bonding will be very much prominent, and because of that, the electron cloud will be shifted to the pi star orbital of CO, and there will be more decrease in the CO bond order. But in case of manganese, since the electron cloud of manganese is very much less, that's why the pi donation from manganese to CO is not that much favorable. So acceptance of electron in the pi star orbital of CO is not that much favorable. So that's why the probability of decrease in the CO bond order will also be minimized. So that's why CO will be the strongest bond in the first complex. So that's why A is the correct answer. Now let's proceed to the next question over here. Now Geldal method is basically used for estimation of nitrogen. So Geldal method is basically used for the quantitative estimation of nitrogen in organic compounds. However, it is not applicable to all nitrogen containing compounds, because this method basically relies on converting nitrogen to ammonium sulfate. Now this conversion of nitrogen into ammonium sulfate will be possible if the orientation of nitrogen is proper. If the nitrogen is properly bonded to carbon or hydrogen atoms in the particular organic compound, then only this conversion will be possible, and then only we can estimate the amount of nitrogen with the help of Gelder's method. Now in case of pyridine or nitro compounds, nitrogen is present inside the ring. In pyridine, it is present inside the ring. In pyridine, nitrogen is present inside the ring. And in nitro compounds, nitrogen is attached with oxygen. In nitro compounds, nitrogen is attached with oxygen. And in azo compounds, nitrogen is attached with another nitrogen. So in this type of bond, in which the nitrogen orientation is not proper, in case of this type of bonds for nitrogen, conversion of this nitrogen into ammonium sulfate is not that much favorable. So that's why Gelder method cannot be used for the estimation of nitrogen in pyridine type of compounds where nitrogen is present inside the ring, or when nitrogen is attached to oxygen, or when nitrogen is attached to another nitrogen. So that's why D should be the correct answer. So in Gelder method, basically the nitrogen atom present in the organic compound, it will be converted into ammonium sulfate, and this is only possible if the orientation of the nitrogen is proper, if nitrogen is properly attached with carbon or hydrogen. But in case of pyridine, since nitrogen is present inside the ring, so that's why it cannot be easily converted into ammonium sulfate. Same for nitro and azo compounds as well, since their orientation and their bonding patterns are not proper. So that's why with the help of Gelder method, we cannot estimate the amount of nitrogen in pyridine, nitro and azo compounds. So D should be the correct answer. Next question. Now in this question, violet color complex, we have to find out the complex, which is getting formed. So during the preparation of lysine extract, sulfur from the organic compound that will react with sodium to form Na2S. Now this Na2S will react with sodium nitroprusside, and after the reaction we will get sodium thionitroprusside as the product. So this is sodium thionitroprusside, and the color of this complex is actually violet. So during lysine test, during the preparation of lysine's extract, sulfur from the organic compound is made to react with sodium. After that, it will be converted to sodium sulfide, and this sodium sulfide will react with sodium nitroprusside. This is actually sodium nitroprusside. This sodium sulfide formed from this reaction will react with sodium nitroprusside, resulting in the formation of violet color complex, resulting in the formation of this violet color complex, and this is actually sodium thionitroprusside. So obviously option C is the correct answer. Let's proceed to the next question over here. Now lysine test is basically used for detection of sulfur, nitrogen, halogen or phosphorus in organic compounds, right? So obviously in organic compounds, sulfur, nitrogen, halogen or phosphorus will be present. So in organic compounds, sulfur, nitrogen, halogen or phosphorus will be attached with the help of covalent bonds. So basically I need to convert these covalent bonds into ionic bonds. So I have to use sodium, then only this covalently bonded sulfur, nitrogen, halogen or phosphorus will be converted to ionic bonds. Now this so basically what we can conclude in lysine test, basically that is used to estimate the amount of sulfur, nitrogen, halogen or phosphorus in organic compounds. So in organic compounds, sulfur, nitrogen and halogen and phosphorus, they will be bonded covalently. So we have to convert the covalent bonds into ionic bonds, and for that we need to use sodium. So that's why sodium metal is generally used to convert the covalent compounds into electrovalent compounds. Since the bonding of sodium, nitrogen, X and phosphorus is covalent in nature inside the organic compounds, so that's why we need to first convert that into ionic compounds with the help of sodium. So that's why D is the correct answer. Let's proceed to the next question. Reddish brown chocolate. So reddish brown chocolate precipitate is basically formed when Cu2 plus reacts with FeCN6 4 minus, and it will result in the formation of Cu2FeCN6. So this is the correct reaction over here. 2CuSO4 will react with K4FeCN6, and after that it will be converted to Cu2FeCN6. This is the complex for which we are getting the chocolate brown precipitate, along with the formation of 2K2SO4. So Cu2 plus will react with FeCN6 4 minus, resulting in the formation of this chocolate brown precipitate over a complex. So that's why A is the correct answer. Let's proceed to the next question. Nessler's reagent is basically used to detect the presence of ammonia. So obviously D should be the correct answer. So NH3 is basically used to test ammonia. So NH3 will react with HgI4 2 minus along with OH minus, resulting in the formation of HgO.Hg NH2I. We will get this precipitate. This is the brown precipitate. So this is the Nessler's reagent over here. So this is Nessler's reagent. Let me write down the reagent as well for your convenience. So this is Nessler reagent. K2HgI4 is the Nessler reagent, right? K2HgI4 plus KOH. So this Nessler reagent will react with any ammonia containing compounds, and after that it will be converted to this product, right? So we will get brown precipitate. This brown precipitate formation of this complex actually indicates there is presence of ammonia in the reactant. Now let's proceed to the next question over here. Now Cadius method. Cadius method is basically used for the estimation of halogen. So in this case, which halogen is given over here? So here the halogen is chlorine. So this is the formula for calculation of the amount of halogen in a particular organic compound. So percentage of halogen is equals to atomic mass of halogen of X by molar mass of AgX, since AgX is the substance over here for which we need to calculate the amount of halogen, into M. M is the mass of organic compound given in the reaction. Here the mass is actually 0.0099 gram. Capital W is the weight of organic compound. W is the weight of organic compound, and this small m is actually the mass of AgX. So percentage of halogen, that is equals to atomic mass of halogen by molar mass of AgX, into m is nothing but the mass of AgX given in the question. Mass of AgX given in the question. So in this case the value is 0.8287, and by W, small m by W is the mass of organic compound into 100%. That is the formula. So what is the mass of halogen over here? In this case we have to calculate the percentage of chlorine. So what is the atomic mass of halogen? That is 35.5. What is the molar mass of AgCl? The value is closer to 143, into what is the mass of AgX given in the question? Mass of AgCl given in the question, that is actually 0.287. This is the amount of AgCl we are getting from 0.099 gram of organic compound. And what is the mass of organic compound over here? That is actually 0.099 into 100. So finally, what is the percentage of chlorine that we are getting over here? The percentage is actually 71.8. So the value is closer to 72. So that's why 72 is the correct answer. Now let's proceed to the next question. how many complexes among the following are paramagnetic? Now in manganese, what is the electronic configuration? Manganese is present in +3 oxidation state, so D5. So this complex should be paramagnetic in nature, right? D5 low spin, so the configuration will be T2G5, Eg0. So paramagnetic because of the presence of 1 unpaired electron into T2G orbital, presence of 1 unpaired electron. Now let's check for chromium. So this is paramagnetic. First one is paramagnetic. Let's check for chromium. Chromium is present in +3 oxidation state. So chromium +3 is actually D3. Chromium mein what is the electronic configuration? 3d5 4s1. If I remove 3 electrons, 3 more electrons will be left in the d orbital. So this is also paramagnetic. This is also paramagnetic. This is actually a high spin complex. Electronic configuration is T2G3. Eg0. Next complex is COEN whole 3. What is the electronic configuration? What is the oxidation state of cobalt over here? Oxidation state of cobalt is +3 because ethylene diamond is actually a neutral ligand. So CO +3 what is the electronic configuration? That is T6, and this is actually a low spin complex because ethylene diamine is a comparatively stronger field ligand, so all the electrons will get paired up. So the scenario of the d orbitals will be like this only. This will be the scenario of the d orbitals: 1 2 3 4 5 6. The remaining 2 orbitals will participate in bond formation. So obviously this is actually a diamagnetic complex. This is a diamagnetic complex, and the configuration is actually T2G6 Eg0. Vanadium CO6. Again in this case, what is the electronic configuration of vanadium? Vanadium is present in 0 oxidation state, so the electronic configuration is 3d5 3d3 4s2. Now because of the presence of the stronger field ligand carbonyl, what will happen? The 4s electrons will be shifted to 3d only, and the electrons will get paired up. So after pairing up, this will be the scenario of the orbital. So 1 2 3 4 5. Since one more electron is present over here, so that's why the resulting complex will also be paramagnetic in nature. So vanadium wala complex is also paramagnetic. Though this is low spin, but still the electronic configuration is T2G5 Eg0. So because of the presence of the 1 unpaired electron, it is actually paramagnetic. Now next complex is nickel. So in nickel, NiNH3 whole 6 2 plus, nickel is present in +2 oxidation state, so 3d8. So for 3d8, what is the electronic configuration? The electronic configuration should be T2G6 and Eg2. So in this way we can arrange the electrons: 1 2 3 4 5 6 7 8. Since two unpaired electrons are present over here, that's why NiNH3 whole 6 is also paramagnetic. And more overall, this will be a high spin complex. Now in NiDMG whole 2. Now let me clean this up first. Till now, how far we have discussed? First one is paramagnetic. Chromium is also paramagnetic. The third one, cobalt complex, is diamagnetic. Vanadium complex, low spin, paramagnetic. Nickel complex is also paramagnetic. Now NiDMG whole 2. Now dimethyl glyoxime is actually a strong field ligand and is also bidentate ligand. So what is the coordination number of nickel over here? Coordination number is equals to denticity of the ligand 2 into number of ligands. Clearly we are able to see there are 2 dimethyl glyoxime ligands over here, so coordination number is 4. So coordination number of nickel is 4, and also there is a strong field ligand, so obviously the resulting complex will be having square planar geometry. Now what is the oxidation state of nickel in NiDMG whole 2? So this is anionic ligand. The charge on this ligand is -1. So I can write down the x plus 2 into -1 equals to 0. So what is the value of x? X ka value is +2. So nickel is present in +2 oxidation state. So what is the electronic configuration of nickel in +2 oxidation state? That will be 3d8. Now since this complex is actually a square planar, that's why what will happen, the resulting hybridization of the complex should be dsp2, right? So this is 3d, 4s and 4p. So 1 2 3 4 5 6 7 8. So all the electrons will get paired up, and the remaining d orbital along with 1s and 2 4p orbitals will actually combine to form the resulting complex. So dsp2 hybridization, and the complex will be square planar in shape. Shape of the complex will be square planar, right? So strong field ligand and also bidentate ligand, coordination number is 4. That's why the resultant complex must be square planar. In square planar, all the electrons will get paired up. So obviously the hybridization of the complex will be dsp2. So again, this is also diamagnetic. Now let's discuss about platinum complex. Obviously, what is the electronic configuration of platinum over here? Not the electronic configuration, what is the oxidation state of platinum over here? So again, platinum is present in +2 oxidation state, right? Because the overall charge of the complex is actually 0. So platinum is present in +2 and chlorine -2 charge. So overall the charge is 0. So platinum +2 basically signifies 5d8. Now 5d metal will always form low spin complexes, and obviously the coordination number of platinum in this complex is 4. So the resulting complex will also be square planar. And what will be hybridization? That will be dsp2. So obviously all the 8 electrons in 5d will be paired up in this manner. 5d, 6s and 6p will participate in bond formation, will participate in hybridization. So the last orbital, that is actually dx square minus y square, 6s and 6px and 6py will participate in hybridization, resulting in the formation of square planar complexes. So all the electrons are paired up. That's why the resulting platinum complex is also diamagnetic in nature. Now CuNH3 whole 4. In CuNH3 whole 4, 2 plus, copper is present in +2 oxidation state. So the electronic configuration is 3d9. Now obviously the resulting complex is also square planar in nature, and the hybridization is sp2d. So this will be the arrangement of the electrons in 3d wala orbital. So 1 2 3 4 5 6 7 8 9. So the resultant complex will be paramagnetic because of the presence of this unpaired electron over here, right? So this one is also paramagnetic. Last example, CuCN4 3 minus. So in this case, copper is present in +1 oxidation state. So 3d10 is the electronic configuration. Again, coordination number is 4, strong field ligand. So that's why the complex will be having square planar shape, and the hybridization will be sp2d. So 3d10 matlab the 3d orbital is completely filled up with the electrons. So all the electrons are actually paired up, and that's why the resulting complex, this complex is also diamagnetic in nature. So how many paramagnetic complex we are able to see? 1 2 3 4 5. So there are 5 paramagnetic complex. So that's why 5 is the correct answer over here. So lengthy question. You have to check each of the following complexes. Next question. Total number of possible isomers of the complex compound. So copper is present in +2 oxidation state, and platinum is also present in +2 oxidation state. So this is the charge of this coordination sphere, and in PtCl4 this coordination sphere will be having -2 amount of charge, right? So Cu +2 and PtCl4 2-. Now, so this is one of the isomer. So there is another possibilities are also present. So second, this is the, so how we are getting this -2 charge over here? So platinum is present in +2 oxidation state. So plus 2 plus 4 into minus 1. The charge on each of the chlorine is minus 1. That's why we are getting overall minus 2 charge over here, right? So this is one of the possible isomer. What is another possibility over here? So I can actually replace the ammonia and chloride ions, right? So sorry, I should write the cationic part first. So I can write down PTNH3 whole 4 2 plus and CuCl4 2 minus. This is one possibility. So 2 isomers we are getting. Now we have to check if more isomers are possible or not. So again plus 2 minus 2. This is the cationic sphere and this is the anionic sphere. Cationic coordination sphere and ionic coordination sphere. Now another possibility is this PTNH3 whole 3 Cl and CuNH3 Cl3. So in this case, what is the charge on this coordination sphere over here? So copper is present in plus 2 oxidation state. Minus 3 will be the charge because of chlorine. So the overall charge is minus 1. In platinum, again plus 2 is the charge. And for chlorine, the charge is minus 1. So the overall charge on the cationic part is plus 1 and the overall charge on the anionic part is minus 1. So again, this is another possible isomer. And there is one more possibility over here. CuNH3 whole 3 Cl, again plus 1, PTNH3 Cl3 minus 1. So these are the 4 possibilities, right? Now you may also think okay, there should be one more possibility like this CuNH3 whole 2 Cl2 and platinum NH3 whole 2 Cl2. But this is not possible because the positive charge will be exactly neutralized by the negative charge. So the overall charge on this coordination sphere will be equals to 0. And the overall charge on the second coordination sphere will also be equals to 0. So obviously both of these cannot coexist. Both of the coordination sphere will coexist only if one coordination sphere is cationic in nature and the another kind of coordination sphere is anionic in nature. So both must be having same magnitudes of positive and negative charges. Then only both the coordination sphere can coexist together, right? So that's why total number of possible isomers are 4. Let's proceed to the next question. A metal complex of coordination number 6 having 3 different types of ligands A, B and C of composition A2, B2, C2 can exist in several stereoisomeric forms. The total number of such isomers. So obviously how we can find out the total number of isomers? That will be equals to number of geometrical isomers plus an enantiomeric pair. Now this is one possibility. AA are cis to each other, BB are also cis to each other, CC are trans to each other. This is one possibility. Another possibility, AA cis to each other, CC cis to each other, BB are trans to each other. So 2 cis, 1 trans. So this one is CC cis, BB cis, AA trans. So all these 3 are 2 cis, 1 trans structure. Now this is all trans structure. So this one is all trans. And the last one is all cis. Right? Now clearly we are able to see there is plane of symmetry. So the upper half of the molecule is a mirror image of the lower half. Because of the presence of plane of symmetry, this isomer is not optically active. Same plane of symmetry is also present over here. Here also the plane of symmetry is present. Here also the plane of symmetry is present. So in all these 4 isomers, the plane of symmetries are present. So that's why they will not exhibit, these 4 isomers will not exhibit any type of optical isomerism. In the last isomer, there is no presence of plane of symmetry. There is also no presence of center of symmetry. That's why it will exhibit optical isomerism So obviously we will get enantiomers. So one will be dextrorotatory, another one will be levorotatory. So obviously, how many non-optical isomers are there? 1, 2, 3, 4. And how many optical isomers are present? 2. So total 6 isomers are present. So that's why correct answer should be 6. So number of GIs is equals to 5. Total number of geometrical isomers is 5. And how many enantiomeric pair we are able to see? So this is the enantiomeric pair. One will be dextrorotatory, another one will be levorotatory. So 5 plus 1, the value is actually 6. Now this is the last question of today's part test. So cobalt is present in +2 oxidation state and it is forming bond with Cl minus, right? So this is the octahedral complex and this is the tetrahedral complex. In both the complexes, chlorine is present in -1 oxidation state and cobalt is present in +2 oxidation state. So obviously for complexes in which the metal and ligand are same, for complexes in which the metal centers and the ligands are same, so we can use this formula. Splitting in tetrahedral complex, splitting in tetrahedral field, that must be equals to 4/9 into del O. Del O is nothing but the splitting in octahedral field and del T is the splitting in the tetrahedral field. For the same, this formula is valid for same metal ligand interactions only. The formula will be valid for same metal ligand interaction. Same metals and for the same ligand, same type of bonding pattern, then only we can actually use this formula. So this is the splitting energy in tetrahedral field and this is the splitting energy in octahedral field. So what is the octahedral splitting energy? 18,000 centimeter inverse. So what is the amount? What will be the value of delta T? So I can write down 4/9 into 18,000 centimeter inverse. So overall 8,000 centimeter inverse, that will be the crystal field splitting energy in tetrahedral field. That will be the splitting energy in tetrahedral field for this complex COCl4 2 minus. So I can rewrite the value in this manner: 8 into 10 to the power 3 centimeter inverse. So x into 10 to the power 3. So the value of x must be equals to 8. So 8 should be the correct answer. So that's the end of the paper discussion session. Thank you very much. So all the best for your next exam. Thank you.